The paper I will be presenting today is called Semi-supervised stance detection of tweets via distant network supervision, and it was published in Wisdom 2022. I will be following this order for the presentation. For introduction, billions of social media users express their stances towards events in their posts. And here, stance means a way of thinking about something, especially a publicly stated opinion. Throughout the paper, they call this way of opinion as stance. Automatic stance detection for hate speech detection, poll prediction, and more has been important, but especially lately, for the importance of political stance analysis has increased dramatically due to increase in partisanship, malicious efforts to distort popular opinion, etc. But not many approaches for this type of text-based stance detection recognize and exploit the fact that text in social network is not doesn't show political stance just in the text. We also follow people with similar opinions with us, and we retweet tweets or reply to tweets with similar ideas with us. So this type of information is actually important. To show an example here, if we focus on user one's tweet, this person tweet about someone, and they said she knew about it beginning of February when Donald Trump talked about it in a speech that she disrespectfully ripped up and more. But in this tweet, this user is referring to someone as she, and we don't know who they are talking about exactly. So in this case, actually, because this is about the US political stance, there can be 5 stance labels for this case. One is pro-Republican, anti-Republican, pro-Democrat, anti-Democrat, and neutral. But since we don't know who this person is referring with she, we wouldn't be able to label it correctly. But if we look at the following list of this user and the tweets they posted during the same time period, we can tell that this tweet would be labeled as anti-Democrat, and the person is referring to Hillary Clinton. So we can use this type of network information to label for stance detection. But we cannot just add this type of feature to the tweet level features because it might add bias, since users can change their opinions but still follow similar people with their previous thoughts. Anyways, so here in this study, they use this network level information, which they refer as homophily, just as a navigator of distant supervision. And homophily means the tendency for people to seek out to those who are similar to themselves. And another problem for stance classification tasks is that there's a lack of human labeled data, because these classification tasks would require a big amount of training data. Usually, semi-supervised and active learning are the common coping mechanisms for this problem. In this paper, their proposed method is called SANS, and it stands for Stance Analysis via Network Distance Supervision. If we look at the overview of the framework, it starts with a few quality seed instances and uses homophily to make a guide for noisy labeling. It uses different ways for tweet text representation and customized feature extraction models, and iteratively trains the component learners. Here there are 3 kinds of textual feature extractors, which I will explain in detail later. These are combined into 2 predictors, and instead of just using standard code training, they use the network information too. And combining network-driven distance supervision and synthetic feature view separation makes the accuracy higher than the other baselines. And also in the paper, they are offering 2 large collections of politically charged tweets with from US and India-based users. And these users' inter-user follow relations, and a small sample data set from these two data sets that is manually annotated with corresponding stance labels. Now, if we look at the related work, stance classification and target-dependent sentiment classification are similar tasks, and we can look at sentiment classification task papers for reference too. However, even though they are similar, the literature of stance classification covers much broader ground. So if we look at the stance labeling strategies in the past papers, they often follow labeling strategy with 3 labels. If there's a target topic, they say pro-target, anti-target, or none or neutral. But if we follow a more higher quality human annotation method, we would have more labels. Like in this example, I said that a tweet can be pro-democrat, anti-democrat, pro-republican, anti-republican, and neutral. And in the paper, they follow this type of labeling strategy too. And most important part of the framework is that they use network dynamics for distance supervision. And it's because previous studies suggest that network-based features provide strong signals for predicting user stances. And code training for text classification is already really popular. In this study also, they analyzed tweet features locally and globally using 2 separate homophily property using 2 separate classifiers, which helps to create distinct views of the data. Additionally, they use the network information in user follow networks as a distance supervision strategy. Now I will introduce the proposed method in detail. First, for the preliminaries, we will define the set of users in a social network of Twitter as the capital U, and UI arrow UJ will mean that the user UI follows UJ, and F of UI means the set of users that this user is following. Capital T is the tweet posted by user UI at time T, and D is the ordered set of tweets over a time period. DS is a small sample from that tweet that is from this data that is manually annotated. And L is the one-hot label for tweets. And here we can define the stance classifier as a mapping. Here C is the stance classifier mapping, and YI here is the YI is the predicted distribution of label probability. And lastly, the theta here is the set of parameters of the model. For classification models of the method, they use 2 classifiers because for code training, they need at least 2 mutually independent views of the data. And they exploit stance homophily to provide another way of incorporating multiple views too. Typically, a tweet consists of a body of text and 1 or more hashtags. For both classifiers, these 2 components are processed independently initially, but they are fused before the final prediction. And the textual body of the tweets can be represented as sequence of words like this, and the hashtags can be represented as a list. Here, the hashtags are learned using a self-attention-based method for both classifiers. I will explain later. And the 2 classifiers are, the first one is convolutional based, and the second one is WSDM based. Yeah. So to start with the learning of the hashtag representations, they use an embedding layer to transform the list of one-hot representations of the hashtags to a list of dimensional dense vectors. Next, they use scale dot product attention to control the contribution of each of these tweets for the prediction task. For these, they compute the query key and value vectors from the dense vectors. And here's the formula for just the query one. The key and value vectors are obtained with a similar approach. And attention weights are computed using these vectors, and the representations for each hashtag is scaled. Finally, they apply max pooling, and the combined representation of the hashtags are computed. But as I said, they use two approaches for the text body representation. And the first one is the convolutional feature extraction method. Again, here two embedding layer maps the one-hot word representations to DW dimensional dense vectors. Then they apply 3 branches of consecutive one-dimensional convolution and max pooling with window size 1, 3, and 5 on this set of vectors. And for each branch, these 3 consecutive operations are applied. ReLU activation is applied to the convolutional output, and then they apply max pooling. And here they represent the sequence as this, and here H0 is the input sequence, and H3 represents the output of the branch with a specific window size. Finally, after these 3 branches, they concatenate together with the hashtag representation too. The concatenated vector is normalized and then forwarded to the prediction layer with softmax activation. And for the by LSTM-based feature extraction, the same embedding layer is used to map to dense vectors. Then a bidirectional LSTM layer maps these vectors into a sequential representation. And then max pooling is applied. Representation of the tweet body is produced, and it's concatenated with hashtag representation, normalized, and passed to prediction layer 2. And these 2 models are denoted as C1 and C2, and they are, and each sub-block of operations for both of the classifiers are followed by a dropout layer to handle overfitting and noise between the layers. And in the training process, SANs consist of 2 repeating phases. First, the classifiers are separately trained on the labeled dataset in a supervised manner, and then the full dataset that has unlabeled data is incorporated to train the classifiers. In this phase, the 2 classifiers generate labels of tweets depending on the network level view for each other. For the supervised phase, it's classical way actually. 2 classifiers are trained independently given the small annotated dataset. Given a tweet label pair, a forward pass on the models computes the predicted class probabilities, and then 2 independent optimizers minimize the loss function. Here, these are the loss functions with here new J is the probability of the Jth class in the ground truth, and V1J and V2J, these mean the Jth class in the prediction of the classifier 1 and classifier 2. And here the W is the weighting function to handle class imbalance. And for the semi-supervised phase, the 2 models generate pseudo labels for the last tweets from FUI. FUI was the following list of the user UI. Here, Y1 and Y2 are the class probability distributions. Next, they select the labels for the unsupervised part from the pseudo-label sets. They compute hard and one-hot encoded labels. Here, these are the one-hot encoded vectors for the labels, chosen labels. They use a majority voting method to choose the hard labels. And additionally, they have a sample weighing function, WU here. Finally, the pseudo labels generated from classifier 1, classifier 2, they are used to optimize each other. The results from these are used to optimize each other. And here, after the class probability distributions are calculated, these are the functions to minimize these two. And here the right hand components are the supervised loss calculated from the annotated label. But if it's not available, it's 0. Actually, to compute the pseudo labels for a tweet, we need the last tweets till that time posted by the users that this user is following. But there can be situation where the following users have not posted a new tweet, but the user in question is tweeting multiple consecutive tweets. And in this case, the forward pass computations are redundant and costly. So they try to solve this problem where they use a sparse adjacency matrix of a follow network. They leverage this to efficiently access class distributions during semi-supervised training. This method allows for scalable training with a focus on minimizing the computational complexity. Here are the parameters for the framework. And I will mention the experiments, but first the dataset preparation is important here too. They focused on political tweets from two demographics, US and India, targeting the opinion dynamics of users around the major sites, political sites in these two countries. Firstly, the US dataset, they call it Stance US, and it consists of almost 60,000 tweets from almost 25,000 users, and it's gathered between January 1st and April 3rd of 2020. And in comparison, Indian dataset, it's called Stance In. It has much more tweets. Here, almost 180,000 tweets from 63,000 users. And they randomly select subset of both of these data and label it manually. And here the potential labels are listed here. For US-based tweets, there's 5 options, and for the India-based one, there are 7 options. 3 annotators do the manual annotation with inter-annotator agreement of 0.84 for the US-based data and 0.78 for India-based data. And to explore the impact of the training data size of the model, they changed the labeled dataset size. They tried 3 different situations and evaluate the performance of the models like this. This is the distribution of the data for the experiments. And they compare the performance of the proposed method with both supervised and semi-supervised baselines. These are, most of them are familiar baselines that we would know. And these are the semi-supervised baselines. They also remove the contextual representation and distant network supervision step by step to see the relative importance. First ablation variant is the just normal co-training framework without the network supervision, and there's no sophisticated label selection strategy. I mean, the label prediction of classifier are not used to train each other. Like in the overall framework, they do this method, but for this, they did not train classifiers using each other's results. Second ablation variant is that there's only one classifier which computes the majority label from the tweets of the followings of a user itself. Also, here the classifiers are trained jointly, but they are evaluated as independent models on the test sets. Yeah, here this table presents the performance of SANS along with all the baselines and the ablation variants. Here SANS show better result than the baseline models for all of the different sizes of the label training data. Here we can see the result. BiLSTM based classifier shows more remarkable results since it has the ability to capture more complex and long distance dependencies in the text body. From the external baselines, BERT performs the second best for stance US data, and BICE performs the second best for stance India data, while these two perform the worst. I think they mentioned in the paper that these perform the worst since they are lacking both the contextual and text network view differences. And also here maybe you realize that in the Indian data, all of the baselines perform poorly because even though in this data set, most of the data is in English, but even though they try to minimize also the different language tweets, there are still more noise in this data. And also the label set is larger than the US data. And here there are there are baselines that show good results, but they require more computation costs. So we can tell that SANS show better result than all of them. And for class imbalance, SANS is compared to the best performing baseline models. Like I said, it was BERT and BICE for the two data sets. And in this one, for dominant classes, actually the baselines also perform even better in this case, for example, or close performance to the proposed framework. But they SANS hold superior performance for handling biased label distribution, because you can see here that the baseline cannot even detect one right answer for the class imbalanced, yeah, class imbalanced data. And SANS is also compared to the purely supervised versions of the classifiers. So for India data, SANS struggles with minority classes too, but still outperforms the two baselines. And if we look at the ablation model's performances, we can see the importance of the distance network supervision. Ablation variant without the network supervision performs drastically worse than the ablation variant without the context-based view difference. For the India data, it's more drastic. The performance difference is more drastic because network dynamics play a more important role for highly noisy data. And to show the stability and convergence of learning here, they trained the model for a sufficient number of optimization steps and monitored the performance of the classifiers on a test data set. Both classifiers generally reach stable convergence after overcoming initial fluctuations. However, these fluctuations are not consistent and vary based on the dataset and the amount of labeled data. For instance, on the Indian dataset, classifier 1 exhibits more performance fluctuation, even in later stages compared to classifier 2. But in the US dataset, C1 showed a more stable convergence than C2. And of course, with larger amount of labeled data, the classifier achieves stability more quickly. They also experimented with multiple different choices of classifier designs for the classifier 1 and classifier 2, and the results can be seen here. And none of these combinations outperformed using WSDM paired with a convolutional classifier. Only the performance of the convolutional classifier with BERT performs close, but still it's convolutional and WSDM combination is the best one. And finally, they experiment with how the amount of unlabeled data affects the performance. And here, the size of the unlabeled data set used is, they use this amount of labeled data. The study explores how reducing the amount of the unlabeled data impacts the performance of the classifier in sense. If we reduce the unlabeled data amount, it has a more pronounced effect on the performance of classifier 2 compared to classifier 1. And the decline in performance with less unlabeled data was more noticeable in the Indian dataset again. And to conclude, since this study uses distance supervision through social network property, it outperforms the baselines, especially in the case of class imbalance. And yeah, with the experiments, they validate this. And their ablation experiments provided insight on the relationship between text-based content and network propagated signals for stance classification. Yeah, so thank you for listening.
Yeah, thanks for the presentation.
Yes.
My first question is that there are two classifiers in the methodology, right?
Yes.
But are they completely independent, right?
Yes, they mentioned like that.
Okay, then we have a hashtag representation, learning representation, right?
Yes.
Then this representation will be incorporated with each classifier,
Yes.
right?
Yeah, here.
Then, mm,
Mhm.
then as a result, we may have the um, based on those classifiers, we may uh, generate the pseudo labels, right?
Yes.
Then my second question is that can you explain how the relationship, following follower relationship between users explained in the page number 4,
Mhm.
how the concept is
Mhm.
incorporated in the learning framework?
Here, because these are the users that user one is following, when this person tweets this, in the same time period, they take the tweets that the accounts that they are following, they take these tweets, and here they use it for, sorry. Yeah, here they use it for the creating the pseudo labels based on yeah, based on these tweets, if they are one of the potential labels, they label the that user's tweet same too. Uh, I don't know if I explained it well, but
Then how the features of the relationship is incorporated with the results of the classifiers before?
mm, uh, I think I couldn't understand. Sorry.
We have the representations obtained by the previous two kinds of classifiers, right? For they are obtained from the contents,
Ah,
right? Then
yes.
we now have the another information for the relationship between users.
Mm-hmm.
I feel that that's the main contribution for this paper, but I'm not sure how this information is incorporated with the previous learned representation from the contents.
Uh, I in the supervised phase, they focus on the they focus on the user's tweet only, and because those tweets are labeled, they can tell how accurate it is. And after this, in the semi-supervised phase, when they are generating the pseudo labels, they are using the most recent tweets posted by the users that this user is following. Um, it like mathematically, also, I don't know exactly how the mapping is here, and they use the tweets from these users, I can tell, but I don't know the mapping. Yeah.
Okay. I feel that the previous
Mhm.
two classifiers are not that novel.
Yes.
I feel that the main contribution for the performance improvement is from uh, the semi-supervised phase
Mm,
to represent the information for the relationship between users. So we need to focus and understand this part of in this paper.
mm. Yeah, I understand.
Okay, then regarding the data labeling, do they annotate all the tweets manually?
They annotate, sorry. Here, this many tweets are annotated only.
Then for the remaining tweets, they uh, labeling
Unlabeled.
them in this semi-supervised way they propose, right?
Yes.
Then how do they evaluate the results for them
Uh,
if they are not have the annotated data as the ground truth?
mm. That part, they don't mention clearly, but mm maybe they show the performance based on only the labeled data. They
Mm,
don't mention it that much. Yeah, I didn't realize.
mm.
But they try to show that the annotation is accurate by uh, using this score, but for the
So
unlabeled,
then they do not show the verification for the labeled data by the semi-supervised way, right?
yes, yes.
Mm.
Mm.
Okay, I think this paper is very easy to follow and understand. I think the paper will be well written and well organized, so we can refer to this paper while you are writing the current CIKM paper. And I also feel that you do not limit your paper in the resource paper, considering this paper. You can also think your paper as the research paper targeting CIKM as well.
Okay. But
And
here,
the most important part in your paper should be the following the overall framework for this paper, uh, including manual annotation and
mm,
semi-supervised way as we are doing. But
yeah,
the distinguishing part for our paper should be the well, verification for the semi-supervised labeled results.
yes. Actually, I read the paper for that reason too, because it's similar, but they did not mention clearly how they compare, how they come with the accuracy here
Mm.
in the experiments. I will check again for the
Mm.
more details.
So I think it's very difficult, so we can solve the problems.
Okay, I will look, Professor.
혹시 다른 질문 있어요? 베이지 학생은 한국말 굉장히 잘하기 때문에 한국말로 질문해도 되고. Beyze, actually, there's a
Mm.
automatic tool to classify the stance bias in terms of the, for example, political. Actually, Jebom and Dion are working on them. So
Mhm.
in this paper, do they mention about them?
No, they did not mention a automatic classifier in not in related work also.
So they just manually label all the tweets, right?
Yeah, they manually labeled.
오케이. 혹시 다른 질문 있나요? 너무 늦은 시간이라 다 졸고 있는 건 아니죠? 잘 들었죠? 오늘은 질문이 하나도 없는 거 같네요. 두 편에